Hello, my name is Luca Pollonini. I'm with the University of Houston, and in this tutorial we'll be discussing principles and main applications of near-infrared spectroscopy. So in general terms, spectroscopy is the study of interaction between electromagnetic waves and matter. So there are different types of electromagnetic waves, such as radio waves, microwaves, light, X-rays and gamma rays. And the matter is essentially any substance that has a mass and that occupies a volume. So it is everything that surrounds us, including our own body. Near-infrared spectroscopy is a specific type of spectroscopy that investigates the interaction between near-infrared light and living tissues. And in this tutorial we'll be discussing specifically human tissues applications. So there exist also different types of light, from ultraviolet light to visible light, which is part of the light spectrum that the human eye is sensitive to, near-infrared light, and also infrared light. The near-infrared spectrum is defined approximately between 700 nanometer and 1000 nanometer, although this range is not strictly defined. Near-infrared light has specific characteristics with regards to the interaction with human tissues. First of all, near-infrared light is non-ionizing, which means that it doesn't possess enough inherent energy to alter the biochemical bonds. In other words, near-infrared light is absolutely safe even for prolonged exposure, unlike ultraviolet light or waves with higher energy such as X-rays or gamma rays. Secondly, the two main light absorbers in the body, which is hemoglobin, which is contained in blood, and water, absorb a lot less in the near-infrared spectrum compared to the visible spectrum. This means that near-infrared light penetrates several centimeters into tissues without being totally absorbed, which gives us the opportunity to illuminate tissues underneath the skin in a completely non-invasive ways, which means that without using needles or endoscopes. Besides being absorbed by tissue, near-infrared light is also scattered or diffused by human tissues, meaning that light cannot travel in a straight path within the tissue, but it is naturally diffused in all directions. And although that prevents the possibility to take highly defined images of tissues underneath the skin, it implies that part of the light is also naturally backscattered towards the skin, where it can be detected by photosensitive devices. Interestingly, the optical absorption spectra of oxygenated hemoglobin, which is the hemoglobin protein bound to oxygen, and deoxy-hemoglobin, which is the hemoglobin protein by itself, are different. This means that if we illuminate a human tissue with near-infrared light at two different wavelengths, it is possible to perform an optical absorption measurement at these two separate wavelengths and use well-known laws of optical physics to compute the changes in concentration of oxygenated and deoxygenated hemoglobin in real time and non-invasively. This is very important because the measurement of hemoglobin concentration provides an indication about tissue hemodynamics, which relates to blood flow changes in human tissues. A near-infrared spectroscopy measurement can be performed in several different ways. For instance, it is possible to use narrow-band optical emitters such as LEDs and lasers and perform the optical detection using wavelength-insensitive devices such as a silicon photodiode, an avalanche photodiode, or a silicon photomultiplier. Alternatively, it is possible to illuminate the tissue with a broadband optical emitter such as a halogen lamp or a broadband LED, and perform the light detection with a wavelength-sensitive device such as a spectrometer. Near-infrared spectroscopy can also be performed with different optical techniques. For instance, in continuous wave near-infrared spectroscopy, the tissue is illuminated with light at a constant intensity, and the backscattered tissue is detected at a reduced intensity. In frequency domain near-infrared spectroscopy, the illuminating light is modulated sinusoidally at radio frequency, and what is being measured is not only the reduced intensity of the sinusoidal waveform, but also the frequency shift and the phase shift, which provides a richer optical information. In time domain near-infrared spectroscopy, the illuminating light consists in a very short duration pulse of light, and what is being measured is the time of flight of the burst of photons traveling within the tissue. The approach to the design and fabrication of near-infrared spectroscopy instruments strongly depends on the application for which it is designed for. One of the main applications of near-infrared spectroscopy is for the measurement of oxygenation of skeletal muscles. In this case, only 1 point of light illumination and 1 point of light detection are necessary. So a NIRS probe can be implemented in a very small form factor, essentially in a wearable factor. Another very active area of applied research is the measurement of oxygenation of the human brain, and specifically of the cerebral cortex. In this case, near-infrared light is shown through the scalp, and it reaches the cerebral cortex when it is backscattered towards the scalp and is detected, and at that point an optical absorption measurement is performed. When the brain is activated by sensing, such as hearing or touching, or when the brain commands a specific action, such as talking, walking, or writing, neurons in very specific areas of the brain, they require a higher amount of oxygen to carry out their function. Therefore, if we place a NIRS probe on top of the brain area that is supposed to be active, it is possible to measure brain activity simply with an optical measurement. This is very important because with a simple optical measurement, it is possible to directly measure brain activity without necessarily requiring a brain scan that is normally performed in the clinical setting. Because this application allows to measure the brain function, it is called functional near-infrared spectroscopy. Functional near-infrared spectroscopy instruments consist of an array of optical sources and optical detectors placed across the brain area. So it is possible to monitor multiple brain areas simultaneously, and by using a specific image reconstruction algorithm, it is possible to produce functional hemodynamic maps like the ones represented in this slide. If you'd like to learn more about principles and application of near-infrared spectroscopy and functional near-infrared spectroscopy, you can refer to the additional readings provided.